Thank you. So, Rick and I have been collaborating in the past 10 years, and on this topic of automatic software architecture measurement and analysis. And while Sebastian was talking, and we were saying we owe him a beer because he's talking about the problem, exactly the problem we are trying to address. And so we summarized our 10 years of research results into something we call a software health management system. And the first thing we want to introduce in this system is a maintainability metrics suite. Okay, and so this is based on our paper published in 2016. Obviously, Sebastian hasn't doing research on that paper yet. Okay, but since 2016, we have been using this metric suite to analyze hundreds of projects, and we are pretty confident it can be used to monitor the evolution of your software projects, and you can tell whether the project is getting better or worse, and how much better, how much worse, and comparing with other industrial projects, and if the project is having a fever, right? We are talking about a health system, and we need a thermometer. So we are pretty confident that, we have a thermometer, or, close one. And the second technology we're going to talk about is the hotspot detection, right? So if we detect the system is having a fever, we have to find out why, right? Is this system is having a pneumonia or just a simple cold, right? So this technology, and we can pinpoint the hotspots in the system. In other words, we pinpoint the architecture or design flaws that is responsible for the ever-increasing maintenance costs. We also call that architecture debt, which means if you do not fix the underlying architectural problem, you have to keep paying the maintenance cost over and over again, just like a real debt. Okay, so in order to help the management to make a decision, that Sebastian said, whether a measurement is meaningful or not, it really can be told by whether it influences your decision-making process, right? So we quantify the cost of each architecture debt, and we also provide methods to calculate the benefits. So in the end, we can provide the management a business case of refactoring. So over our experience with many industrial collaborators and 252 open source projects, and we already influenced the decision-making procedure in almost all these companies, listed here. And next, we are going to introduce the general workflow of this whole process. So what we do, what data we collected, and what are the tool churn we used. And in the end, we are going to report our most recent experience with 8 ABB projects. Okay. First of all, this general workflow including like 3 steps. These 3 steps we repeated in multiple companies. First, we have to collect the data from their repository. The data including the source code repository, including revision history, also including their issue record, such as the Jira record, Bugzilla record, or work item in their Microsoft Team Foundation. And with all this data, and we first, transform all this data in a standard form, which we will introduce. We call that design rule space, which can be visualized and using a design structure matrix. And with using the design structure matrices as the unified modeling models, and we further, can do these automated analysis, including measurements and hotspot detection and cost and benefit calculation. And the last step, of course, and we usually give service and collect feedbacks and phone calls, right? And we ask them, does this influence your decision? Are you going to refactor? Do you realize where and when and how to refactor? So we generally received very positive feedback. Okay. And okay, this is the closer look of our tool churn, and our original tool, we call that Titan, and we now developed Titan into a new tool suite we call Deviate. And these are the input of the deviates. Oh, I'm sorry. Input of all the deviate accepts. For now, given the source code repository, we first use understand as our preprocessor to process and generate the dependency information within the source code, so that we don't need to worry about which programming language we are dealing with, right? We leave that to understand. So understand will output us a general XML file and with all the dependency information. And the second, and we will extract the revision history from either Bitbucket or GitHub or SVN record. And the third type of input is their bug report, like which bugs are reported and how they are fixed. All this information from the standard repository. And using this source code dependency information output by understand, and also using the history, we generate two kinds of design structure matrices. The first design structure matrices representing the structural dependency among source code. The second one, will model how often two files chain together in revision history. And given this information, and given the standard representation, that is DSM, and we further do, our metrics calculation and hotspot detection. We have two ways to detect hotspots, and given the hotspots we detected, we can further do the cost and benefit analysis. And eventually, we have a semi-automated tool to put together a report and get it back to the practitioner. So from the user's perspective, they provide us the repository, the history record, and the issue tracking system. We give them back a report. Okay, the report will contain their metric score, their percentile ranking with all the other projects we have, and their hotspots, and why these are hotspots, and how significant these hotspots are. And in the end, we take surveys and phone interviews with the developers. So that's the general process. And a little bit more about the data accepted by the toolset. And we have significantly improved the toolset. Now, if you not using Git or not using SVN, it's okay. We provide a standard XML dependency format. So if you can write your own script to translate any dependency information to be the input of deviate, so that you can analyze any type of dependency, even beyond source code or revision history, right? You can do build dependency, dynamic dependency, as long as you can give us input following the standard format deviate requires. And some companies, they do not have very complete history information. It's okay, we just mirror your source code. Some companies do not have issue tracking system. It's okay, we can detect some of the architecture problem, but not all. So that's why these information are optional. The history and issue information are optional. Okay. So given this information, I want to introduce briefly the model we use as the input of our tool churn deviate. We call that design rule space. And this is also the new model we proposed in our XC 2014 paper. In that paper, we proposed to model software architecture as a set of overlapping design space. And each design space can consist of a meaningful subset of the system files, and these files must have some kind of architectural relation. So you may ask, what exactly is meaningful? Think about this. It's actually very intuitive. Any non-trivial system must have multiple features, right? And we can consider each feature as its own design space. And each system must have more than one design patterns applied. And why can't we just treat each pattern as its own design space, right? And similarly, each concern, each logging, each tracing concern, every aspect that people concerns can be extracted and modeled as its own design space, right? So naturally, a file can belong to multiple design space, and naturally, a software architecture should and can be modeled as multiple overlapping design space. Okay, so in this case, we can flexibly extract and view any aspect of your software system of any design space. And for each of the design space, and we can visualize that using a design structure matrix. And for those of you do not, not familiar with the concept, a design structure matrix is just a square matrix. Its columns and rows are labeled with, it can be labeled with any design element you care. But in this case, we just label the columns and rows with the file names and in the same order. And a style, marking the cell representing the dependency between the file on the row and the file on the column. So this cell's labeled as extension, which means file 5 extends file 2. Okay. Similarly, and this one is saying that file 7 implement file 6, which means file 6 is an interface, right? And you may already notice that. And in this DSM I'm showing here, only the polymorphism relation are modeled, right? So in this case, it's the DSM extracted from the source code of a small calculator. The small calculator applied multiple patterns in their source code. And just to look at this polymorphism design space, we can clearly see very distinguishable modules. For example, here we have a BNF module because it's a parser, AST module, visitor module, filter module. And these independent modules, in the last, I was trying to show how to make this point. It doesn't point. It's just to emphasize, don't point. And so the blue box along the diagonal are independent modules because they don't depend on each other. And the red blocks on the top, we call that design rule modules because they influence other parts of the system. And as we can see, all the important interfaces in the system are aggregated into the top modules, including things like the pipe and filter interfaces. Okay, so we have a special algorithm called DRH to aggregate any DSM into this shape so that we can identify, which files are most important, are the leading file, and which modules are independent. So this is another design space from exactly the same system. This is the design space of the visitor pattern design space. And in this visitor pattern, as you can see, the key interfaces in the visitor patterns are the visitor interface, the file 2, tree visitor, and another is the AST node interface. These are the two key interfaces of an observer pattern. And so as you can see, in this design space, it has multiple relations, but representing a pattern design space. But they are from exactly the same system. And another example we see is that using DSM, we can not only representing structural relations, but also their co-change relation. Look at these two boxes that are highlighted. There is an additional number 25 in column 1 and row 5, which means that these files are changed together as recorded in variant history for 25 times. Okay, and this is okay because number 5 depends on number 1, and if number 1 change and number 5 change 25 times. Okay, but there is another number I highlighted is 20, which means file 6 and file 4 change together 20 times, but they don't have any structural dependency. So we call this phenomenon, which I will introduce later, called modularity violation, so that you can see, where the structure is deviating from their evolution history. Okay, so this is our model, design structure matrices, and as we can see, we use DSM to representing various design spaces in a software system, and we can model structure and evolution information simultaneously. Okay, and using this DSM model, and now we are ready to, go on with our various analysis. Okay, and the first one, measurements, measure and monitor. Second one, pinpoint the hotspots, and finally, quantify the design data. Okay, first of all, I want to introduce our new metric suite. Okay, decoupling level is a new matrix we proposed in 2016. Okay, just 2 years ago, published in ICSI. And in the rationale, we can only have time to talk about the rationale of this matrix, is to measure how loosely coupled source code is. Okay, which is the complementary to the traditional coupling-based measure. Representative one is propagation cost, proposed by Harvard Business School, Dr. McCormack in 2006. Propagation cost measure how tightly coupled your source code is. Okay, so there are so many metrics already, right? We have coupling, coherent, and CK, and all kinds of metrics. If you use SonarQube, you can be overwhelmed by the number of metrics and measures they provide, right? Why we are having another one? Because we observe that none of the existing metrics, so-called metrics, are real. Okay, what are the property of real metrics, like the meters and bathroom scale? Okay, we identified three major properties of a real matrix. First of all, it has to support, comparison, right? If I compare the DL score of my project with Chrome or of Apache, I should be able to know that which one is better and by how much, right? Non-existing or prevailing matrix like coherent can do that. Second, it has to support evolution monitoring, right? Software keeps changing. Is this getting better or is it getting worse? By how much, right? None of the existing metrics can do that, like, Sebastian just said, right? And they are not influencing the decision making. And finally, we really like to see a maintainability health chart. Okay, we're all familiar with the general health chart. I take my daughter to her doctor, and the doctor will tell me that your daughter is 28th percentile of all the girls of her age. Okay, I'm fine because I'm short too. I'm okay, right? But I have a general idea, where my daughter's height is ranked among other girls. I want to do the same thing for all the maintainability. We want to see, this project is, its DL score is like 60%, and it's ranked about, 40% percentile, comparing with the other projects. Then that will give the management, a very straightforward judgment, how well the maintainability their system is. So we hope we can collect enough data and to form this health chart. Now we have about 300 projects or something, and if any one of you are willing to contribute to this database, please contact us. Okay, so these are the three major properties we think a real matrix should have. And we do believe our decoupling level have these properties. We cannot say it's as precise as a bathroom scale, right? But it's pretty close. And the rationale of decoupling level is that first, we consider a truly modularized system should be like a Lego system, right? Composed of many and independent, replaceable modules, small, changeable, evolvable, and composable. They can be put together, right? And if a system is highly maintainable, then it must have a large number of these true modules, right? And connected by their design rules, simple rules. Interestingly, Lego system has very simple rules, right? That's the size of their holes. Okay, we think the good software system and a highly modularized one, highly maintainable one, should contain large number of independently, truly evolvable modules connected by simple rules. Okay, so based on this rationale, and we went further and to calculate the coupling level. First, we cluster a DSM into this shape, right? And the larger part of the bottom layer, which contains the independent modules, the higher its maintainability. And for the upper layer system, the fewer the dependency they have, the better its maintainability. And we don't want a module have too many elements. We don't want a module to be too large, too complex, right? So the smaller the module, the higher its value. So eventually we put together a score, putting all these elements together. For details, please refer to our ICSI paper, 2016 paper. And this is our decoupling level, and in order to compare and contrast with existing metrics, we also use propagation cost proposed by Harvard Business School researchers. And the propagation cost is also based on the design structure matrices, but the difference is that they calculate the direct dependency among the source code and calculate all the possible indirect dependency among source code. That is, they calculate the maximum transitive closure of the first matrix and see, eventually, how many direct and indirect dependency together, and that is to the total number of cells. So in this case, the propagation cost is 100%, right? Which means that any change in one of the file is possible to influence any other file in the system. So their metrics measures, how tightly coupled a software system is. And one limitation of propagation cost is that it's very sensitive to the size of the system. Right, as you can imagine, because the denominator of PC is the number of files square. Okay, so a little bit change in the number of files that will influence the PC significantly. In order to make meaningful comparison, and this is a data set from data set we published in 2016, only contains 129 projects, and we rank these 129 projects based on their DL score and the PC score. The red one is a DL score, and the blue one are the PC score. As you can see, if a system's decoupling level score is 74%, it can be ranked around 80 percentile, which means it's better than 80% of other 129 files. And if a system has a PC score of 70.7%, it can be ranked in 80 percentile, right? So the higher the percentile ranking, the better its modularity. So at least the data shows that PC and DL are perfectly complementary to each other. The higher the PC, the lower the DL, and vice versa. And this is a closer look of these. We separate the industrial open source projects and commercial projects, and we can see that the average DL for commercial project is 54%, and average PC is 60%. And both open source and the closed source project have some really high maintainable system and really low maintainable system. The lowest one can be 14%. DL and 15% DL for commercial project, right? But for commercial project, we also find some really high maintainable systems. They have really high DL, 93%. Okay. So given these numbers and these benchmarks, and we are able to rank any software system. So this is from one of our industrial project we analyzed, 1 year ago. And in this industrial project, its DL score is 29%. And comparing with all the other 129 files, is only ranked the 10th percentile, which means that this is pretty low, very hard to maintain, And so this, the practitioner, the global architect of this system came back to us saying that this is unbelievably realistic. And even adding 2 lines of code in this system will need 2-digit memos, code to code. Okay, so to them, this system is already terribly hard to maintain. And they felt that, but they have no way, no number to indicate that. And once we give this number to the company, and it was immediately accepted. And now they realize how bad their system is, right? Previously, they just have intuitive feeling, oh, this is bad, very hard to maintain. But they don't know how bad it is. Now they can tell they are worse than 90% of other systems, right? That's pretty bad. And this is another project we did with an IBM project. And in this project, we measured 29 release of the same project, exactly the same project. And we measured the DL score of all the 29 releases. And we observed 4 transition points, like from release 1 to release 2, the DL score increases and decrease, and increase again. Okay, so then, we got back to the chief architect of that project. We asked him, we found 4 transition points. Is that meaningful? Does that tell you anything? And the architect said, oh, this is, again, very realistic. From the first version to the second version is the one that they transform from the research prototype to a real product. They really cared about architecture. And from the second, downgoing transition, and it is where they keep adding new features, and technical data is accumulating over time, so they can feel the maintenance becomes more difficult. Adding new features is getting harder and harder. The interesting one is the third one. And when I showed this to the architect who happened to be my part-time student at Drexel, I was saying, something wrong going on at this time period. And he said, it shouldn't be. I refactored that. I refactored the system during that time period. I'm expecting to see the DL going up. Why it's going down? And so we went ahead and looked at their DSM and how things change between the 2 releases. And then he said, oh my God, my developers implemented the pattern all wrong. Okay, all wrong. The refactoring was very unsuccessful. Okay, and at the last time period, and he said, people really cannot put up with the technical data anymore. So they spent a few months and to clean up their source code, so their DL goes up. Okay, so this is all retrospective, and we are pretty happy. These 4 transition points realistically reflected how their software, quality getting better or getting worse. Okay, so we feel like any company should be able to use this number to monitor their evolution, the evolution of their projects. How much time do I have? I'm good? Okay. Am I good? Oh, okay. Okay, and okay, given these numbers, and again, the practitioners are not happy with the fact that some of their projects only ranked 10 percentile, right, of all the projects. Then they go further ask, what's wrong. So we provide, tools to identify these 6 types of architectural flaws. So this is also published in our WIXA 2015 paper. If you are interested, please take a closer look. And I only want to show the first 3 one, unstable interface, and the modularity violation, and the crossing. And we have shown that, in our WIXA paper, we have shown that these flaws are highly correlated with bugs, changes, and churn. Okay. And unstable interface, so this is one of the design space, and we identify this file too as an unstable interface. What does that mean? Which means that this file is highly influential. It influences, almost all the other files in this design space, right? But in the meanwhile, look at the numbers in each cell. It's very high, which means that this file changes together very frequently with all of its dependents. Okay, which is very bad. You have a key interfaces that keeps changing. That's really a bad sign. So we call this phenomenon unstable interface. Second, crossing. What is a crossing? Cross is not something good. So we identify files that has high fan-in and high fan-out, which means this file has a lot of dependents and depends on many other files too. What makes things worse is that it changes very frequently with all these other files. Okay, if it is at the center of the cross and never change, it's okay. It's not that, right? Not generating penalty. But in the meanwhile, if it's changing frequently, look at these numbers, 10 and 6 and 5, and which means it is really in trouble. So this is the second type of flaw our tool can detect. Third, modularity violation. Look at these files. They have no dependency. They are so loosely coupled if we measure from using propagation cost. Okay, but if we add their code change history, things are so different. Look at this DSM. It has all numbers, no labels, which means these files change together all the time. Whenever one file changes, the other file changes with it. Okay, it is no, but they have very little structural dependency, which means there are strong implicit dependencies among these files. So this project is from SoftServe. So we verified with their architects. Indeed, you know, there are some implicit dependency among these files. Some kind of code logic is copy-pasted, you know, everywhere. Okay, so and with this, then we that's the flaw. That's one way we detect what's wrong with your system. And another technique then we did is architecture root. What is architecture roots? So based on our study of large number of systems, we realized that the more error-prone files are, the more likely they couple together. Okay, and it is usually because the wrong relation among these files that is propagating errors through large number of files. So we capture these wrong relations among error-prone files and put them together into a special design space we call architecture roots. And so this is our 2014 paper. ICSI 2014 paper. And here we have, from this study, we have realized that, you know, files, if the design space is led by a very error-prone file, then the whole design space is error-prone. And usually, you know, you don't have to look into many design space. Usually 5 design space will cover more than half and even 90% of all the error-prone files, which means that highly error-prone files are likely to be architecturally connected. And finally, if you look into their design space, the root space, they always have many flaws. So this is one root we detect from JBoss, and as you can see, and file number 13 aggregate, you know, file 18 to 19, and in the meanwhile, file 19 to 18 aggregate 13, cyclical dependency, right, which is not unusual. And but look at these numbers, you know, behind the aggregation sign, 14, 20, 17. It is a very expensive cyclical dependency, right? This is not just a cyclical dependency; it's a very expensive one. And then you look at these numbers, very high numbers, which means the first file is also an unstable interface, right? So this is one root we detected, and it has multiple architecture problems. And so this is, you know, from our paper 2, we realized that, you know, in JBoss, if we look at only 5, these roots, that you can find 52% of the most error-prone files, which means the files change for bugs 5 times or more. Okay, and this result is very generalizable, and see the JBoss is the best one, right? If you look at 5 DR space roots in Eclipse, you can find 83% of most error-prone files, right? Then you can see how these errors propagate among each other. And quantification, you know, now we can see, oh, each of the root can be considered as an architecture debt, right? But management needs numbers, right? We give them numbers. We give them DSM. They don't read. Okay, let's give them numbers. So this is some output of our Deviate tool. And we summarize, you know, all the costs, you know, are incurred by each type of flaws. For example, click in this system, click itself, you know, there are 26 cyclical dependencies, and these clicks, you know, generated, you know, bug fixing churn, length of code, 16,000, which covers about 45% of all the churn spent to fix bugs. Okay, so which means about 50% of the bug fixings are about these cycles, right? And then for each you know, click, we can give more detailed information output by our tool churn. And it's saying that the most severe click in the system is click 1. It has 99 files, and itself, you know, have incurred, you know, bug churn 4,000 lines of code, right? So this gives people a very straightforward way to rank and prioritize which flaw to fix, right? Which flaw deserve more attention. Okay, and further, okay, given that we already calculate the cost, and in SoftServe we also did the experiment of, you know, asking the architects, you know, do you want to refactor them? And if you refactor them, and what is the refactoring cost? They estimate that for us. So eventually they estimate refactoring all these debts need 14 months. And then we also estimated expected savings by comparing, you know, average cost of other files, and we realized that, you know, the savings will be 41, you know, man-months, and comparing with the cost of 14 man-months, and you can expect over 300 return on investment. Okay, so this is the business case the management would like to see. if we want to justify, spend some time to do refactoring, and this is the table they would like to see. Okay, so these, so far, I summarized, all the techniques, we did in different companies, the measurements, metrics, and pinpoint hotspots, and also quantify architecture debts. So this is our very recent experience from ABB, and we analyzed, we applied all the 3 techniques and applied to 8 projects developed in different locations, India, USA, and Switzerland. And we went through the general process, right? We explore the research question, is this meaningful? Does this whole framework, deviate framework, help you decide when, if, when, and where to refactor? Does the suite, the metric suite is meaningful? Do you think the comparison with other project, it's, makes sense? And whether the hotspot is really where things went wrong, right, from the developer's perspective. And these are some results, right? These are the percentile DL score and percentile ranking of all 8 projects. As we can see, this project is the worst. It's the worst. And they agreed and loved it and convinced that something needs to be done. Okay, and eventually, as we will talk later, the first 2 files for project are really small, only have 100 and 300 files, except these 2, and all the other 6 are undergoing refactorings based on our information. Okay. And this is one of the routes, and we deliver to them. And this route, as we can see, has unstable interface and file cycles and modularity violation. And these files we capture together with this one DSM are the most error-prone files. The highlighted cells are their percentile ranking in terms of error proneness. So all the red one are top 1 percentile most error-prone files, right? So again, this proves, again, over and over again, that most error-prone files are likely to get together, okay? And eventually, we give them numbers, right? And these are the first architecture debt and how much cost, has incurred, the debt penalty incurred in these existing, problems. And we also estimated expected benefits. That's the extra effort spent comparing with average files, right? In this case, we didn't even have to ask them how much man-months you need to spend to refactor because they are already convinced. They start refactoring immediately. So basically, they were saying, oh, yeah, indeed, these are the problems. We do have these flaws, and we have to fix. So, the rest are straightforward and tedious, right? And we give them a survey, ask them the 6th question. Does the metrics make sense? Does that reflect your understanding of the system? Does the flaws really tell you what's wrong with the system? Does the architecture root meaningful, for the development team? And yeah, we got positive answers for all of them, and all the 8 projects verified information provided is closing the understanding gap with the management. And the development team and the management team can talk to each other based on these numbers, and they already began the refactoring process. And second, they all like the quantifiable results. They need numbers, right? Like Sebastian says, we need numbers. And these quantifiable results allow them to prioritize which flaw to be fixed first, for example. And finally, 6 out of the 8 projects already start refactoring. The other 2, they have really high DL score anyway, right? They feel good, and they are small. Okay, lessons learned. And it is possible to do automatic and objective assessment and quantify architecture quality. And the results are really enthusiastically received by projects. And the 6 of projects already being refactored. We are happy with that. And ABB is now incorporating DV8 into its development process. And some of the practitioners want to check their source code and every day, every build, so that they don't want to see a sudden drop of DL, right? That will be a bad sign. Or they want to see the sudden drop of DL so that detect that and fix it immediately. Okay. Conclusion, you cannot manage if you cannot measure. right? And our Deviate tool suite, have made the measurement of design complexity, flaws, and easy and less labor intensive and repeatable. This has been repeated at least in 4 companies. We are very confident about it. And incorporating these technologies into build process ensure a rapid feedback with supported data, right? We give the data to the boss and developers, and they both look at it. And finally, this will lead to a better architecture. So that's it. And we are trying to commercialize this tool and through the idea. And everything is under construction, everything, okay? So feel free to visit the website. It will change every day anyway. And any questions? And also we have office hour tomorrow from 1:30 to 2:30.